I'm Tyler Hashimoto.
I'm Nic Smith.
I'm Jacob Lansfield. This is Lab 6, off-axis aberrations, and we are in the Wednesday night lab from 6 p.m. till about 1 a.m.
Coma is a third order wavefront here, described as W131H rho Q cosine theta, showing as linear dependence with your field ring. This image here illustrates how coma works. You have your off-axis ray bundles that are incident on the lens, producing coma, so your sagittal and tangential rays are X-ray coma. Analyzing the coma a little closer, we see that we have our pupil and our image plane. The change in pupil locations, the black versus the blue, lead to a change in magnification, which are the black and the blue here as well. And because we know that coma has a quadratic relationship with pupil location, that rays entering the extreme points of 1 and 2 will form a coincident point here in your image plane, 1 and 2. And we're measuring the tangential coma from the top of the ice cream cone back to the paraxial focus point. These here are the transverse ray errors and sagittal ray errors of coma. We see with the transverse ray error, epsilon y, is quadratically dependent on the pupil location. So you have your two extremes, say epsilon y1 and epsilon y2. They're going to be the same in your ray errors at the two different pupil locations, which is what we showed earlier. And that just shows even function, and there is no central coma.
Astigmatism is an aberration that is caused by the power in the horizontal and vertical meridians being different as ion changes. As you can see, we have the tangential rays that will form a horizontal line at the tangential focus, while the sagittal rays will form a vertical line at the sagittal focus, while in the middle of the two foci is the medial focus, which forms a perfect circle. Positive astigmatism is when the tangential rays are focused closer to the lens than the sagittal, while negative astigmatism is when the sagittal rays are focused closer to the lens than the tangential. L is the length of the line image at the sagittal and tangential focus, while the medial focus forms a circle with the diameter of L over 2. Delta Z is the overall length from the sagittal focus to the tangential focus, but at the sagittal focus it's 0. But at the tangential focus, we can find it using this equation here. Here we have astigmatism, which is W222, which corresponds to H2 rho 2 cosine squared. And in this field, we show H is equal to 1, where it shows the astigmatism line going across the pupil location at Y is equal to 0, showing a slope. However, if H is equal to 0, which is at on axis, we will have a straight line, which shows no. So here we have the transverse ray equation, which shows us that at epsilon y, we have our astigmatism, which we can solve for. However, at epsilon x, we have epsilon x is equal to 0, so therefore we have no astigmatism on the x-axis.
Here we have the test setup with the heating laser aligned to the Kepler beam expander, collimated, which has been bounced off of the mirror, deviated 90 degrees, through the Hartmann mask, through the testing lens, through the microscope, and onto the screen.
Here we have the mesh image, which forms after focusing all 5 points from the Hartmann mask, which is then imaged through the microscope, which forms a diffraction pattern similar to the 2D version of the Young's double slit experiment.
For part C, we set up an off-axis field, H equals 1 we called it, by shifting the microscope 5 millimeters. And we did this while blocking all the holes in the Hartmann mask except for the center one, and then we adjusted the mirror until, as you see down here, the crosshairs line up completely with the center of the spot. And then for part D, we kept it at this off-axis field, and we covered every hole on the Hartmann mask except for the left one, and then the right one at separate times, and then adjusted the microscope until the crosshairs lined up with the spot again. And we got the same result for both holes, which was 40 microns, which was our tangential coma, and we realized that it was symmetric just like the theory said, so our hypothesis was correct. Then we tested sagittal coma by covering all the holes except for the top one, and then the bottom one separately. And we got that A equals B equals 0 for both of these. So sagittal coma was 0, just like the theory says. And then using that ratio of tangential over sagittal, it approaches infinity, just like the theory said. For part E, we used our same full field off-axis to measure the astigmatism. And we did almost the same thing as for measuring the coma, except instead of covering all the holes except for 1, we covered all the holes except for 2, the 2 horizontal ones on the edge for tangential, and the 2 vertical ones on the edge for sagittal. And then we adjusted the microscope until the 2 beams lined up, formed one spot, which was aligned with the crosshairs. Did that for both of them. And then the difference in the microscope positions was our delta Z, which was 0.16 millimeters.
For the results for our calculations that we measured, we started with the delta Z equation so that we measured that, and then solved for W222, which we came up with 1.3 microns, which we then plugged into our epsilon y equation, which is the astigmatism minus the coma, because that astigmatism and coma dominate on an off-axis system. And we measured 0.1 millimeters, which gives us our coma, which is 4.7 microns.
These are the ray fan plots that were given from Zmax. On the left you have the field of 2.5 degrees, and on the right you have the ray fans for the 4-degree field. Here are our measured data of tangential coma, sagittal coma, and astigmatism. We then have the wave area coefficients and the calculated data as shown below.